All right, last video for section 2, I promise. Just one other thing we want to look at with these parameterized curves. We just looked at finding the length of a path. The last thing we need to figure out is going to be the area of the surface. So if we do have a path that creates a surface, it'd be nice to find the area of that using the parameter functions instead. All right, so just kind of remember, this was back in the day, that to find the surface area, we would integrate over 2 pi, and then this was kind of the informal way that we wrote out what that integral is. The integral 2 pi y ds, where ds represents a little tiny space of the arc length. And then the y, of course, was just the vertical values there. Another way we did it was with the rotations, which is where the 2 pi stuff is coming into play. Okay, I'm just going to go ahead and I'm not going to bother with doing what we did in the last video with all the partitions and writing it all out. I'll just give you the formulas. There's 2 different ones. If you have revolution about the x-axis, then... Ooh, come on, computer. Then your formula is this. So your surface area is going to be the integral across the parameter, so from a to b, of 2 pi, the y function of your parameterization, and then it's going to be the square root of the derivative of your x function with respect to t, plus the derivative of the y function with respect to t. Trying to get in the square root there. And then dt on the end. Okay, so very similar to arc length, and very similar to the surface area formula that we have from chapter 6. So surface area, the integral from the parameter a to b 2 pi y, where y, remember, is a function of t, times the square root of dx dt squared plus dy dt squared. And then if you have revolution about the y-axis for your parameterization, then it's going to be this. So same stuff. Still going to be from the parameter going from a to b, still have that 2 pi out in front, but now it's going to be x. And then this is the same, so the square root dx dt squared plus dy dt squared dt. All right, and then we're just going to do like a really quick example of finding this. Well, it would be another kind of goofy example. So let's say we want to find the surface area of a circle revolved around the x-axis, and these are my parameters. So x equals cosine t, y equals 1 plus sine t, and then we're going to be looking at the interval 0 less than or equal to t less than or equal to 2 pi. Okay, so this is just a circle. It has a circle with radius 1 that has moved 1 unit in the vertical direction. So just think of it as like can I draw on here? Surely there's a way of just drawing. Oh, it's not worth it. Okay, just imagine a circle with radius 1 that has moved 1 unit above the origin. That's all there is to it. Okay, so we're trying to find the surface area here. This is being revolved around the x-axis, so we're using this formula. I'm not going to copy it back down since it's right up top there. We're going to do the integral. This is going from 0 to 2 pi. Okay, we're going to have that 2 pi out in front, and this is going to be times y, which is 1 plus sine t, times the square root of, oops. All right, so then we're going to have dx dt squared, so that's going to be the derivative of cosine, which is negative sine, but negative sine squared is positive sine. That plus the derivative of y with respect to t, which is cosine, but that squared is cosine squared. dt. Okay. Same thing's going to happen as it did in the last video and the last example that I just did. Sine squared plus cosine squared is just 1, so that whole square root just disappears. Another thing I'm going to do here is I'm going to go ahead and pull out the 2 pi to the front of the integral. All right, so moving the 2 pi out in front, all we have left on the inside is the 1 plus sine t. Remember that square root's now gone. All right, and then just antiderivative stuff. So we have the 2 pi out in front, and then this is going to be 1 is going to go to t as the antiderivative. Sine is actually going to be negative cosine. All right, and then again, we're evaluating this between 0 and 2 pi. I wish there was a nice way for me to do it. I'm sure there's got to be. If I write it like this, does everybody understand what I'm saying, right? This should be going down from 0 up to 2 pi. Okay, if I plug 2 pi into this, I still have the 2 pi out in front. If I plug 2 pi into the t, I'm going to get another 2 pi. Minus, if I plug 2 pi into cosine, cosine of 2 pi is positive 1. That minus the 2 pi that's out in front, and then plugging 0 in. So that's going to be 0 for the cosine, minus cosine of 0 is positive 1. All right, and then just simplifying down, 2 pi distributed into here is going to be 4 pi squared minus 2 pi. And then we're going to have a negative 2 pi times negative 1, so we're going to have a plus 2 pi. And of course, those 2 pi's cancel out, and we just end up with 4 pi squared. Good. And I hope this makes sense to you, because remember, the area of a circle is just pi r squared. Sorry, that's not going to make sense, is it? We're doing surface area stuff, right? So not the surface area, or not the area of the circle. We need to know the surface area of a sphere. Because that's, remind me later. Don't do it now. The surface area of a sphere, right? So I'm going to have to Google. Surface area of a sphere. 4 pi r squared, right? So if we have a radius of, that's not going to help. If we have a radius of 1, which is what we have in our example, then we're just going to get 4 pi, which is not what we got over here. Why did I have an extra pi in there? Ah, crud. Hold on. I'm not even recording anymore. Okay, I did some research. I'm dumb. That's why it wasn't working out. So here's the problem in the book, right? X is cosine t, y is 1 plus sine t, and then we're revolving it around the x-axis. The reason that I was so wrong is that I was thinking that we were just revolving it on its own plane and creating a sphere, but we're not creating a sphere. We're creating this weird donut-looking shape. This donut-looking shape does have a surface area of 4 pi squared. So I should not have found the surface area of a sphere, because that was not what the surface is that we were even creating. If my circle is up here with a radius of 1, then when I rotate that around the x-axis, I'm creating a donut. So oops, my bad. The answer is 4 pi r squared, so we did get that right. Just goes to show that math is a lot smarter than I am.